Well, hey, everybody, welcome to our webinar today on how HALT works and why you need it. I'm Steve Laya here at Elite, and I'll be your meeting host and a co-presenter a little bit later on in the webinar here. Our keynote today is Adam Bahret of Apex Ridge and Adam Bahret Consulting. So again, welcome everybody. Glad you're here with us today at lunch. I'm also here to kind of manage this webinar a little bit. So if you're not seeing the presentation or if you're having any kind of difficulty with the audio, let me know. Send a chat maybe. I do have everybody muted, so if you need to connect with us, just send a chat. And we'll be checking the chat for any questions that might come up. I know Adam wants to make this a very kind of interactive presentation, which I think is a good idea too. Before we begin with Adam, I wanted to mention just a few words about Elite. If you don't already know about us, we're a large test lab in Downers Grove, Illinois. We're just west of Chicago. Pretty diversified in industries that we serve and the testing that we perform. We cover a lot of automotive, large vehicle type of applications, military, commercial aviation, a wide range of industrial and consumer products. So we're pretty diversified. We perform HALT testing, the topic here for today, but quite a few other environmental stress tests, vibration, temperature, humidity, enclosure ingress protection, photometry for light measurements. We do a lot in that space. We're one of the largest EMC labs in the country. We cover all of the industries I just mentioned and others. We're a regulatory test lab and a certifying body. So we do a lot there too. Yeah, let's keep going here. Adam, he's going to be Adam and I. We're going to be monitoring the webinar. Are going to get any chats or inquiries that come up? We'll try to answer all of these questions as we're kind of moving along. But if you have any additional things that we don't mention here, we will we'll follow up with emails afterwards. We've got some future webinars planned, so yeah, stay connected with us if you can. And we'll both Adam Bahret, he does a lot of online training, so keep connected with Adam and his newsletter as well as Elite, and you'll see of additional training like this coming out. And let's start the presentation. So Adam, let me turn it over to you, and we'll get it going.
Okay, great, thank you. So I'll start off. I'm Adam Bahret. I founded Apex Ridge Reliability Engineering Consulting 10 years ago. In that time, I've served many companies across multiple industries like Hyundai Motors, Keurig Coffee, Boston Dynamics. Written 3 books on reliability engineering. How Reliable is Your Products, about the reliability toolkit. Reliability Culture is about how to implement the Design for Reliability toolkit in product development programs so you get the maximum ROI. Devastate the Competition is about how to keep it connected to the program goals and business goals. You can, of course, go to my website, adambahret.com, or follow me on Instagram. I like to put lots of funny little videos and different things on there. These videos called Atom Bombs are 60 seconds of some thought or thing going on or project I'm doing, which I think you'll enjoy. But I've started this year a series of handbooks on specific reliability tools. What I wanted to do was take these different tools and give them each a little short 60-page, kind of very easy to read and digest overview. So the Perfect HALT test is available on Amazon now. It's the kind of thing you can read while waiting for an airplane, or even, have it as kind of a pocket reference if you're going to be jumping into a test soon. All right, so let's jump in here. What is HALT? That's what this is all about today, is you understanding HALT. And I really do encourage you to, if you can, unmute yourself. I don't know if there is that option. If not, putting in a message that you'd like to share something, please do. I have no interest in just talking for an hour, for this whole period straight. I'd love to interact and to direct this to be to the areas of interest to you. So HALT is this. It's getting back to being this kid. He's not looking to pass a test, looking to test to fail. You want to just create as much destruction as you can. You've done a successful HALT test. If there's firemen involved, safety cones, safety tape, and there's a smirk on your face. That's what we're trying to get back to. This sounds like I'm being funny, but I'm not, because that's how we learn. When we were younger, we broke things apart, took it apart, with no regard for how it's going back together to learn about it. And we slowly have had that taught, educated out of us. But there is value in that, in having a tool like that in your product development program. So let's look at what the actual definition of HALT is. It was first coined by Dr. Greg Hobbs in the 1980s, and the definition was it's done to ruggedize a product and obtain large margins over the expected and use conditions, uses all stresses which can cause relevant failures. Stresses are not limited to field levels or the types of stresses you see in the field. Now, the acronym HALT stands for Highly Accelerated Life Test. I kind of have a problem with that because I feel it's a very poor description as to what it is. It has nothing to do with life. It doesn't tell you anything about the life of the product. In fact, you very knowingly give up that opportunity to measure life so that you can see failures very quickly to use for design improvement. So it's really about failure. Is it a test? I don't think test is a good word. It's an exploration, because test is implies that something we want to pass. We've been trying to pass tests our whole life. If you do a HALT test on a product and you have no failures, that's how you fail. So I really believe it's a HAFE, highly accelerated failure exploration. If you ever see me and you say you like HAFE, I know that you're cool, and we can do some kind of dorky fist bump or something that geeky engineers will do. But for the rest of this presentation, I will call it HALT testing. But do keep that in mind. It's a name that can be very misleading to what it's really about. And Dr. Greg Hobbs said this himself too. He kind of regretted giving it that name. So use case and environment, these are critical when we're doing any kind of test, because this is what connects us to performance in the field. We want to feel free to abandon the stresses that we have in normal use, because that will constrain us from really getting a chance to understand what the failures are. Now, it might seem kind of counterintuitive to induce failures that aren't associated to normal use, but there's a lot you can learn about by root causing a failure, no matter how it was caused. You might find, put very high vibrations on your product and test and cause a fracture in it and say, well, this thing doesn't see 40 Gs of vibration when it's sitting on a shelf, when it's in normal use. But that root causing that might help inspire a design change that can actually mitigate failures when you have poor plastic injection molding. So a totally different cause, but you have found an area where there is vulnerability, and you might find opportunities to do really simple robustness improvement design changes early in the program. So even though the 1980s is when Dr. Greg Hobbs coined the HALT philosophy, as I said, it's very intuitive, and actually in my constant curiosity about product development, found an example of what I would consider to be one of the first real HALT tests. And this occurred back in the 1960s during the NASA Saturn rocket program. And the motor was the Apollo, for the Apollo was the F1 motor. And they had a really serious challenge in developing this motor where the thruster cones would crack. They would vibrate and break. And this became really serious and very likely to actually impede the program progressing at all. And, thus we wouldn't have had the moon landings when we did. So it wasn't until an engineer suggested putting little explosive charges in the cone and blowing them up and looking at how they fractured and use that as design input to improve the design against it resonating and breaking. So this was rather radical and seemed to be blindly destructive. But when you consider how expensive it was for them to do an engine test, by comparison, destroying a single cone was quick and inexpensive. And they actually were able to, in analyzing these fractures when they blew them up, design a cone that would not only not crack, but it would naturally dampen out any resonant frequencies, which is a big deal because the conditions it operates under change dramatically from atmosphere to space. And you can still see this today when you look at videos of rocket launches. You can actually see how the cones flex and move and dampen themselves out. So this came from applying the HALT philosophy, where, it really demonstrates how you obviously putting literally dynamite on your product and blowing it up is far beyond the intended use case, but you can see how it yielded this critical information at a critical time. So what's the HALT process? It's generally in 4 steps. We're looking to select stresses and apply them and continue to increment them until we get failures. And as I said, the purpose of the failures is to analyze them. Now, this can occur during the test where you actually stop the test and do analysis and maybe even experiment a little bit, or maybe take that unit aside, start testing on another unit, and then to examine and analyze that unit when you're there. Of course, a lot of the analysis will happen when the test is over, back in your actual design process. But you might find opportunities to change things and do the same stresses again and see what can improve or cause different performance. So it's all about that process where we go from stressing, failure, analyze to improving our design. So what are some common stresses? As we said, you can select really any stress you like, but some common ones are using temperature extremes. This is where we will ramp the temperature either up or down until we get responses. But what I mean by responses is the performance changes somehow. And you might have issues that are when you remove the stress, the performance recovers, or ones that actually, permanently damage the device. And you can even go farther beyond that by isolating where those failures occurred and progressing. So if it was a hot temperature, you might put cool air on the area where you had the first failure mode so you can progress farther. Another one is temperature ramps. Temperature ramps are what we're looking to do very fast transitions because we want to create mechanical stress from the expansion and contraction from the temperature change. We have vibration is another very common one because vibration creates a lot of physical motion that causes fatigue and can induce failures. And we'll talk a little bit more about how the HALT chamber is very different with regard to both temperature ramps, temperature extremes, and the vibration than a lot of the other tools that we see in a normal test lab. And then we can combine any of these stresses. Once we've learned about where the limits are, we can take the stresses close to the limits before failure occurs and then do combinations with other stresses to see if we get other unique types of failures. So one thing that's very unique about a HALT chamber is that it uses liquid nitrogen and very high wattage heaters with big fans on it. So when you compare this to a regular environmental chamber, which uses compressors, similar to the way refrigerators, air conditioners, and some heaters work, the liquid nitrogen is there in the high wattage heaters for the fast transition, because that is a really critical stress for exposing failure modes. And that's for 2 reasons. One, when you have dissimilar materials, the thermal expansion coefficients can be, very different, causing a lot of mechanical stress as they expand at different rates. The other is when you have a mass, you're going to get a thermal gradient across it as the temperature transitions, right? Steady states when it reaches an equilibrium temperature throughout, but the transition, you can have very big changes causing a lot of internal mechanical stress. So we want that fast transition rate, which we can't get from a normal environmental chamber, even though normal environmental chambers can actually go to very far extremes. Now, vibration, this is interesting and where a lot of important technology is in a HALT chamber. A type of vibration that we all are very used to is electrodynamic vibration, and this is in a single axis, and it's usually one frequency that we can control. So what you'll do is you will take that product, put it in an orientation for the axis you want the vibration to occur, and a lot of times do a sine sweep, right, where you're increasing and decreasing frequency, looking to find one that resonates or is an area of frequency that's of interest, based on a use case. This is what we expected to see in use, so we're curious what happens here. Now, you can induce failures with that, of course, but that's going to be a very long process because, of course, for each one of those, sweeps, you're going to need to do a different axis. You might do different amplitudes of G's for the different sweeps, different, frequencies, and none of them are in combination. So the kind of table that does this is a lot like an audio speaker, right? It's electrodynamic, where it's a magnet and a coil, and it actuates it in a single axis. So it's, and it controls the frequency. So that's really exactly what an audio speaker is. Now, a HALT table is designed to do 6 axes, which means all 3 linear axes and all 3 axes of rotation, and broadband frequency, which means multiple frequencies at the same time. So when we're increasing the stress, we're only increasing one factor, which is the G's, the amplitude. Everything else is already turned up as high as it can be. It's happening on all axes, rotation, and a lot of frequencies at the same time. So this is where some of the magic of a HALT chamber comes in, and it is within the design of the table, because that's a tall order to get all those axes, rotations, and all the frequencies, because a table, obviously any device has, it's going to want to ring at a set frequency. So a lot of work goes into creating one that can transition all that energy and all that complexity to the product. So that's why HALT chambers are really key when you want to use vibration to explore failure modes. So, as I described, we're going to do in different steps, hot, cold, and the transition. So it's important that these are separate, because we will use this information in several ways. With the hot step stress, you'll come up to a point where you, like I said, will have a performance variability, and you're going to want to remove the stress to see if it recovers. That's a soft fail. Whereas you then will progress to one where it doesn't recover. Now, these limits, can be very helpful in other parts of the product development program. At some point, you're going to want to set specification limits and functional limits and destruct limits, and know where those are for everything from determining how the product can be used, knowing if you want to make design improvements to satisfy a design requirement. But most importantly, when you're doing quality assurance testing, you are going to be using stresses a lot of times that are beyond the normal stresses. So it's really important to know what those margins are, and that information can come directly from HALT testing. So you'd have that for hot step stress, cold step stress, and the transitions, which are determined by the hot and cold step extremes, because obviously we don't want to transition. We're looking for the change to be the stress and not the extremes. So I'd like to stop for a second, and with all that information I just shared, are there any questions or comments? I would love to just get a few comments. Do we see anything in the messages there?
Not yet, but I think you're doing fine, and it's a good beginning to the conversation here.
Can you hear me?
Yes, I can hear you. Did somebody?
I was just curious. Yeah, I was just curious, when you're doing HALT and you have a multi-axial environment for vibration, but you have one GRMS that you're reporting back for control. How does it calculate that GRMS when you have 3 axes going?
Yep. So the RMS stands for root mean squared, which is, I don't know if you do like finite element analysis and stuff like von Mises stresses, when you do like a finite element analysis plot with a CAD model and it's showing stresses and kind of, giving you a color or contour. But obviously those stresses are in all different directions. So like the von Mises stress is creating a value based on the cumulative values in those different directions, usually some kind of exponential relationship. The root mean squared for the table is the same. So effectively, you aren't hoping to have something that you would absolutely compare to the outside world, because that's not the objective. We've decided to abandon relating it to use cases. What we're looking to do is find a value that we can use so that we can, in a controlled way, go up set steps that we've predetermined. And also, if we want to return to a specific stress, we have a value to return to. So this root mean squared method works very well for that.
But how do you account for the x, y? You say x squared plus y squared plus z squared and take the square root?
I'm actually, off the top of my head, I don't recall how it's calculated. It might be that simple.
Is there a triaxial accelerometer somewhere measuring that?
Yeah, so there's accelerometers. There's ones attached to the table which measure it and bring it back to this software, the control for the table, which is taking whatever that signal is back and doing the conversion. You also can put accelerometers on in the device. Now, the orientations, you will find different values in different orientations, but a lot of that is because of how the product's moving. So if you are looking to do something comparative to see, well, how much energy is getting from the table to the product, you'd want to make sure it's in the same orientation as the one in the table. But you will have some energy loss, or you sometimes you can have ringing and amplitude increase. But again, it's all comparative. We're not looking to measure something absolute to compare the outside world. It's all comparative to what we've done. So as long as you aren't changing your setup while you're doing the test, the comparison should be, in the correct proportions so that you could replicate something or compare it to another part of the test.
Great, thank you.
Yeah. Let's get one more question. There must be another one.
Yeah.
Does anybody have?
Oh, yeah, and Tom, I guess what I was going to say, this is Steve Laya here. Yeah, we do have a little bit of data on that too, right? So we've experimented with our table, and we'll look at what the our HALT table, for example. One of the items that we look at is called throttle, right? It's just a scaled number between 1 and 100%. And 100% will give us about 60 Gs as measured by that control accelerometer. But we've put onto our table then triax accels, because we wanted to answer that exact question that you asked too, is, how does that control accelerometer apply or compare to these three axes? Because we wanted to explain or at least convince ourselves too that, hey, are we getting acceleration in each of three axes? And indeed, yeah, you do. When we put our accel on the table as a response accel, yeah, we're seeing pretty close. The G's that are reporting, the G level that's being reported for that accel on the triax, those three numbers come relatively close to each other. They're different from what that control is, right? Our input to the table. But yeah, we have some. We certainly have some data here that we can share at the end of the presentation here that kind of illustrates that point. I'm sorry, was there one more question that came up too?
I do have another question, but I want to hog all the question time here. So I've seen people try to put some fairly massive things in a HALT chamber, and it just seems like the HALT is best for small components where it doesn't have a lot of thermal inertia, for example, like, because it's hard to thermal shock a big, 10-pound box of electronics, right? So are there guidelines on how do you know what's too much?
So you're not limited to the chamber. The chamber is just a tool. And so once I wanted to do HALT using vibration on a large insulator device, and it was probably about it was a solid composite. It was about 3.5 feet tall, weighed a ton. And there was no way this was going to work in a chamber. So we actually designed a big metal frame that we had out in the parking lot with huge pneumatic cylinders. The frame looked like the kind of thing you use to stop a train. It was about that size, those big triangular frames by the time we were done designing it. And used it to pound the hell out of this thing out in the parking lot. I mean, we sold tickets. People came and wanted to see this test. So there's no bounds to how you can, okay, NASA used dynamite, right? There's no bounds to what you can do to try to induce failures. The HALT chamber is a tool that's very convenient for a lot of smaller products. But if you're coming up to the limits of what you think the chamber can really deliver the stresses you need, feel free to go get a sledgehammer, right? And calibrate it, put it on a pivot, and calibrate how high you drop it. Really anything goes.
Okay, that's very helpful. I think a lot of people, when they hear HALT, they automatically think of a HALT chamber and not necessarily the philosophy or the concept behind it.
Yeah, it's very true. That's why I start off with the Apollo example, right? And you'll see in the book I give some details on the little workbook on that one I did in the parking lot, and it really is open to absolutely anything and gets really fun as well. At some point. So see if you can talk your company to bring dynamite into the lab. Great, thank you. Thanks for those questions, Tom.
Can I
All
ask
right. Go ahead.
one more question, or at least sort of a lead into maybe something you're going to talk about? So at what point do you say, okay, I've done enough HALT on this product. Now I'm ready to do some more correlated type validation testing? Where do you draw the line on that? But you don't have to answer now.
No, it's a very important question. So that's about understanding all the tools in the reliability toolkit and understanding what it is you're looking to accomplish at that moment, which includes program constraints, right, of time and money, and using the right tool at the right time. It'd be a little bit like, I always make the analogy, like it'd be asking a car mechanic, well, when do you use the 13mm wrench? And he's like, when I have to take off a bolt that's 13mm. I don't know what time of day that's going to be or whatever. I just know all the tools in my toolbox. I know what I'm trying to do, and I know which tool to pull out at the right time. So within the product development process, there's a couple points where there's these opportunities to use HALT, but you have to remember what's the reason why I'm doing it. The reason why I'm doing it is I want to get some feedback and observations and understanding of how the product works and doesn't work, because I'm looking to make the design more robust. So if your product is in the manufacturing prototype stage where everything's locked in, molds are made, doing HALT testing at that point, no, it'd be a very minimal return, because most of the things you find will be of interest, but you're not going to be able to connect it to a use case and say there's a really high risk that this is bad thing's going to happen. They're like, you did that at 30 G's. So it's unlikely it's going to drive any change at that point. When you first get your hands on a prototype and you can, say, hey, look, everybody, within like 3 days in a lab with relatively short money, if you give me 2 or 3 of these prototypes, we can come back with a lot of interesting observations about how it failed that we may or may not have expected. And now's the time to do it, because we can make changes. And you might find some really cool things and then say, hey, let's go back again. And then, so your question is to when do you stop? You might stop when you say, you know what, we don't have time to go back again. We've already learned a couple of really good things. We seem to be getting diminishing returns. It's going to be entirely dependent on what makes sense for the program.
Great, thank you.
Yeah. So at a quick, high level, what does HALT do? We're looking to quickly discover these failure modes, understand, design margins, which can be pretty interesting for other aspects of the product development program. We're looking to just release as mature a product as we can. I kind of call it blind robustness improvement. Blind because we don't know exactly how much more robust we made it for the use case, but we know we've made it more robust. And we're looking to just, before we spend all that time trying to measure reliability, how do we improve it as quickly as possible? And this can be a great reduction in time and cost, even though it feels like you're adding a step, because it's much more likely to pass the test that you do need to pass later, because you aren't finding these issues out down the road. You found them earlier where they're easier and quicker to address. So you have to remember, HALT's not something you want to pass or fail, and it's a tool for discovery. So you should be in a discovery mindset and in a part of the program where you have the opportunity to use discoveries to make improvements, and that can be harder later on. So what does that kid want? Do they want to test to pass? No, they want to test to fail, because we're not looking to measure. We have to remember that when you test to pass, you're looking to measure, and there are lots of tools for measuring, but it's using HALT, and which surprisingly I see very often people want to measure performance. You end up kind of getting the worst of both worlds. Because what you do is you begin to limit what stresses you can use in HALT, because they have to be applicable more to use case or something that translates to the real world. So you're not getting as much from HALT. And also, it's not really going to be that great a measurement, because you've constrained it to a lot of the criteria for a HALT test, where it would make more sense to do a test that's more rooted within all the full parameters of what you want to make your statement on. So we're testing to learn. This kid wants to be a detective. You want to create an accident scene, and you want to be a detective using the observations there to improve the design. So that's the mindset we have to keep reminding ourselves of. So I like to show this graphic quite often, because I find it creates a really great foundation for a lot of discussion with regard to reliability. Many of you will probably recognize the bathtub curve there in the middle. And so the bathtub curve is a graphic that shows kind of a general characterization of how products fail throughout their life. So It's very exaggerated, but to make the point. And there's three major phases. You have the first part where the failure rate's high and comes down very quickly. And this is generated by manufacturing defects that quickly fall out of the population. And why, we look to, obviously in real life, you wouldn't have it be this, this high. It would be hard. You'd have a bad yield. But we do quality screening in here to keep whichever ones do occur in-house. And also that's why you give warranties, because you want to, commit to your customers that if there's manufacturing defects, that's on us. Then the second part of the curve is the flat part there, the bottom, which is when we talk about reliability, really what we're discussing. And this is the random failure rate during use from normal use stresses that interrupt, how the customer intended to use it. Then in the end, we have wear out failures. And this is, I don't even like to call them failures. It's a design characteristic. It's how the life ends for a good product, right? It's a predictable degradation until the product doesn't function any longer. And it was, intended if it occurs as expected. At the top here, you see I have this gradient from orange to blue, of course, orange to blue, for improved reliability and measure reliability. And that's because the test toolkit, I feel really, each one has a unique combination of these two objectives. And what you can see here is that HALT testing is all the way down on the improved side. And it's sacrificed the opportunity to measure to give you so much improvement information so quickly. And what we see with HALT testing is interesting is that it can help in actually all three parts of the curve. What it can do is, it can lower the random failure rate during use life. It can shrink, the defects that occur in manufacturing because you've increased robustness. Like I said, you might have that vibration failure that as you address it with changing the features, now, a less complete plastic injection mold that normally could have caused a failure now won't. And it can extend life because a lot of the HALT tests are accumulated stresses. And as you address, these types of failures you may have not been aware of before, you very likely could be extending the life of the product. So it helps in all three areas. So it's very powerful. And the earlier you can do it, the more you can take these observations and improve all three parts of this curve. So within the product development program, HALT testing can fit in many places. Something I like to state is do it as early as you can. I mean, you can even do HALT testing before you have a prototype. You might have areas of your design that are where you've done the new technology development, and you can create some kind of a component or set of components that represents that and just HALT that. You don't need the whole product. You have a lot of legacy information on the rest of it, and it's kind of matured through the fact of been a part of your legacy products. But the HALT testing can be used with the area where you don't know a lot. That's what it's about. It's about learning about design functionality you don't know. So if there's some way to take like maybe your legacy product and jam your new technology, aspects into it, even in a very kind of awkward way to where the rest of the system is just now a test stand, do that and get it into a HALT test as quick as you can, because the earlier you get these observations and bring them back to the team, the more likely you are to use them to improve the design. But just because you've done HALT testing once doesn't mean you should not continue it through the program. Come back and do it again when you do have, the next generation of prototypes and see comparatively how they fare compared to the first run of testing. Or maybe you've made changes that you get in an entirely new failure mode that you didn't expect and is kind of eye-opening. So it's a test that is relatively short to do compared to other tests, usually within 3 days, relatively inexpensive. So there's no reason to not try and fit it in as many times as you can. Now, of course, the later you fit it in, you are getting to see more of the response from the final design, but you also have much less opportunity to implement these, design improvements. So my favorite is when you do it multiple times through the program and get the best of both worlds. Now, HALT also works as a great facilitator or catalyst, I'll say, for other tools in your product development program to have a bigger impact. HALT testing, with finite element analysis, can be really interesting because a lot of times in finite element analysis, we aren't 100% sure how boundary conditions are affecting performance. Well, you can actually take an extreme temperature or extreme vibration or whatever other extreme stress you've done, and use it to anchor the FEA model, so that it gets a similar response. HALT testing with an FMEA, failure modes effects analysis, is where we're identifying areas of great risk. It can be really neat if during an FMEA, an action coming out of it is, hey, let's do a HALT test on this area of the design and bring that back to the next FMEA and help us understand more where we said we see a lot of risk. HALT testing can also identify interesting relationships you didn't expect between stresses and failure modes. And this is helping with one of the harder parts of design of experiments, which is selecting the stresses you want to do your statistical work with, where you are looking to be very precise and understand the relationships. But HALT testing might be the insight to help you select the right stresses to do less iterations. Now, you heard me mention before about quality testing. So in quality testing, generally 3 levels, right? You have burn-in testing, which is the most basic, just kind of turning on the product, seeing that it works within regular specifications. You have environmental stress screen, which are far elevated stresses, looking to, to expose those quality failures quicker. And then you have HASS testing, which is highly accelerated stress screen. There actually is no way to create an effective HASS test without having done HALT testing earlier to understand the relationship between the extreme stresses and how the product performs. So HALT testing actually becomes a requirement for advancing your quality program and your production screening process. So there's a couple stages for acceptance of HALT. As you can imagine, a lot of times when you take a designer who has been passionately working on their design, this is their baby, and you say, yeah, yes, I understand this product is used, in a lab in a very controlled environment with the dust is, dust is controlled, people are wearing masks, the temperature is controlled, and I want to take it and vibrate it to 30 Gs, and they're saying, no, you can't do that. That doesn't make any sense. You're going to create, of course, you're going to create failures, and what am I going to do with that information? And they're in this mindset of they want to test to pass. They want to pass all the tests. This is what they've been looking to accomplish. And then if you drag them kicking and screaming through this, the second stage is they might see something that they totally didn't expect. I didn't expect it to break that way. That's really odd. And it might give them some interesting ideas about how to change the design. And you might change it not just to make it more robust. It might be an interesting opportunity for cost reduction or some other factor that's important to them. And they'll implement that idea. And then the fourth stage is always the ones who most passionately push back against it are the ones who then come and say, hey, I have a new design. Can we do HALT testing right away on it? Because they see how valuable it is. So what we want to remember is that this kid gets it. This is who you want to be. And this one too, and hopefully you. I've always loved HALT testing, as you can tell from building things that have to be run out in a parking lot. Yeah, it's really a great tool and, very versatile. And when it's understood and used, where the opportunities are, the gains are absolutely tremendous. So before we move on to Steve's examples, are there any other questions or things I can answer?
Hey, Adam, just real quick, there were a couple of questions that came in. One of them was, will this recording be shared to the participants? And yes, the answer is yes on that. So we're recording it now, and that'll be made available for everybody on when we're finished up here. So thank you for that. The other question was, in addition to general quality testing and inspection for HALT, does it make sense to use HALT to qualify an alternate supplier, kind of as a quick way to compare robustness of the same assembly from 2 different suppliers, one known good?
Yeah, so there's going to be a lot of factors around that. Again, that's the 13mm wrench thing. When should I use a 13mm wrench? So you can't just say that is a standard way you have to compare 2 suppliers, because you may not be comparing any of the factors that really matter between them. But if your product is used in extreme to elevated temperature, and the use cases and things that can happen can be highly varied, and you have a second supplier that is the area of technology why you're committed to your first one, taking it through those HALT high step stress the high temperature steps may be a way to do a really good quick comparison. Is this one as robust as the other one? Yes, we're way beyond use case, but simply seeing that the second one, new supplier, doesn't have as much margin as the first one does, might be an interesting indicator to bring back to that decision. But HALT testing is never going to definitively tell you go, no go with another supplier. It's just another tool in your toolbox as you choose to examine the factors that are most critical.
Thanks, Adam. Thanks, Michael.
So I highly encourage anybody to reach out to me. I'm happy to talk about this to any great extent. You can email me at adam@apexridge.com. Yeah, of course, you can just go to the website and find a link to reach out to me. And yeah, I encourage you to sign up for the newsletters. You can find that on the main page as well. I try to send out a couple fun things per week. Everything from a Monday graphic that's just an idea to you'll get a summary newsletter from Reliability Rhythm. We do our newsletter on Friday, as well as other interesting information. So Steve, do you want me to go to those 2 slides you had?
Sure.
Okay.
Yeah, when Adam and I had talked about the presentation, I thought, well, let me just give maybe a couple of 2 slides on some common questions that we receive here at Elite about HALT. And one of them has to do with, how do you hold the part in the test? And Tom, I think one of the questions that you had asked, I thought led to this slide as well. Here's an example of kind of a smaller device, and only one of those products mounted in our HALT table here. We test lots of different types of products. Some of them are in larger enclosures. And yeah, that's always a little bit of a question, right? What is the best way? How many samples do you test? What's the best way to secure them? How large or how small the samples can be? And honestly, we learn something on every HALT that we do. One thing that is important is fixturing, and also understanding how fixturing might relate to the table. So this table is as Adam had shown here, it's a resonant structure, right? Underneath this table, on our table, we have 9 pneumatic hammers that strike it. Each impact produces a response on this resonant table. When all 9 of them are going, we get this very homogenized, random, quasi-random vibration on the table. If you put large and heavy devices on there, or if you put a very large fixture on that table and you constrain the movement of that table, you're going to change the character of that HALT test. Maybe not significantly, but this is one thing that we always ask our customers. And when we talk to them, one thing that's important is fixturing. So here's kind of an example, and I didn't bring the data with here. I'll share that later on too. But you can see at the center of the table there's there's a triaxial accelerometer on one of those standoffs right in the middle of the table. And then you can see on the picture on the left, there's another response accelerometer, a triax, on that printed circuit board too. And in that way, we can kind of see how the transmissibility of vibration is from the table to that part. And on the right, we moved that accelerometer to a, right on that printed circuit board. But when that circuit board was held within the plastic enclosure of that little residential thermostat. And I don't have the data here. Again, I'll send it to you later. But when you see the data, when it does come out, you'll notice that there's a pretty big difference in the level of vibration that's coming into that unit on the right, because that was not really a hard fixed PCB in there. We really didn't have a good way to hold it constrained and still have the unit operate. So these are some of the things that we do on every project here, is to try to think, how do we get the stress of the test to the test item? So fixturing is important. Also, exposure of the electronics is important too, because you can see there the HALT temperature changes come from air that's directed from a plenum to the parts. And in that way, we get some very quick temperature ramp rates on the part. So really what we hope to do when we talk to clients is to try to expose as much of the electronics as possible, taking off whatever coverings we can while still maintaining, the operation of the device. Sometimes you can't take the electronics out of the enclosure, otherwise they won't work. So we work for an optimal solution here where we try to get the vibration, we try to get the temperature or whatever the stress is to the part without the enclosure or the mounting impeding that stress from getting to it. And I don't know, Adam, if you had any other thoughts on your take on fixturing or test setups as well.
Yeah. Yeah, again, same thing with the test itself. The test, fixturing, be creative. I mean, you can, for a system that you can't take out of an enclosure, a hole saw can be a pretty magical tool to create some Swiss cheese of that enclosure and get a lot of airflow. As you've shown here too, you have the ducting, and I brought smaller ducting to then tape onto the bigger ducting, and you can actually channel the smaller ducting inside some barrier you have to flow. So be creative, and you'll kind of make your own kind of cool little toolbox of go-to hacks as you do more and more of these.
Thanks, Adam. Yeah, next slide. So on the next one here, another question that we get is how should I run my HALT? There is a relatively accepted process for HALT, and Adam illustrated that on one of his earlier slides, where we generally start with a temperature exposure test where we'll ramp down in cold temperature. We usually, there's no particular hard, fast rule on this, but typically we'll start with a cold step stress test, and we'll lower temperature, maybe 5 or 10 degrees C per minute. I'm sorry, not per minute. We'll lower the temperature. We'll dwell for 10, 15 minutes, 30 minutes, long enough for the product to reach equilibrium at that temperature that we're at. Continue on colder and colder until we reach some sort of soft fail and or a recoverable failure. Understand is what the nature of that is as best we can. And as Adam mentioned, if necessary, you might have to sort of pacify that failure and maybe even blow a little bit of warm air on the part of the design that's being affected, so that we can continue on going and exploring colder and colder temperatures and other potential anomalies that show up. So yep, continue down cold, then repeat that process going hot, thermal shock, as Adam had illustrated too, and then move into the vibe and combine steps. So one of the things that we were trying to track here are, what sorts of things, and right, what's this Pareto chart that we're coming up with, where we're finding failures as a result of certain stresses. We find that they're all valuable, but I think as this data is kind of showing, it does seem to be when you certainly when you combine these stresses and you're really pushing that part not only on some of those potential failures that are susceptible to cold or to hot, that when you apply that vibration, that really does find those potential weak points. So there are tests where we don't find fault. We have listed here no fault found on 12 out of 15 of these cold steps. No fault found on 10 out of 16 hot steps. When we look at that as HALT practitioners, we try hard to find fault with products, as Adam's kind of mentioned there, that we're working on. But in the time that we have in that test, we may not be finding faults, but that doesn't mean that there's a temperature sensitivity. It just may mean that at some point after exposed temperature, hot temperature, for example, a different type of failure mechanism may eventually fail the part, right? There are short-term stresses, and then there are long-term degradation of electronics and other parts that in HALT we we may not find because we're just not applying temperature long enough to find those faults. There's another tool for that. You know, there might be a long-term, long duration test at high temperature that evaluates degradation as a result of that applied temperature stress. Same thing for vibe. You know, we may not have found a vibe fault when we did. There was 5 projects where we didn't find any vibe problems, but you know, if we would have continued on with that vibe, eventually we would have found those faults, right? You could apply vibe, right, for you know 6 months, and eventually something will fail. But within this test constraint that we have, yeah, we're always looking for ways to produce those bits of information. Sometimes fixturing helps. Sometimes you know, the nature of the product, you know, might just not respond to the HALT that we're providing, the HALT vibration that we're providing. So every test really does need an initial, you know, coming together of the design team, of the HALT practitioners to really flesh out what's going to be the most appropriate test using this chamber, and you know, perhaps some other tests that will get you the information you need about your design. Adam, any other thoughts
No,
on?
it's great. No, that's great. Yeah, like I said, happy to continue the conversation with anybody that wants to reach out. You can email me, adam@apexridge.com, or, you know, like I said, on my website, you can easily connect with me. But yeah, thank you everybody for attending. I appreciate the questions. I hope it was informative. And yeah, just get on your HALT journey. It's easy to get started.
Awesome. Yeah, if there's no further questions, then yeah, absolutely. We're going to follow up with an email summary of questions and the items that we discussed today. I'll probably send out a couple of other slides that came up here to everybody just to kind of show you. I think, Tom, you asked that question about how HALT varies on the table and in each of the 3 axes. So I'll make sure that that's on our follow-up reply here. We usually send out a short survey too, asking for your feedback. And if you guys have some suggestions for us, we'd love to hear those. Any future topics that you'd like to know, learn about, let us know as well. And again, as Adam said, if you've got a product that requires these services, you know, we're more than happy to help. We'll get on a Teams call, review it with you, and see if we can help you on your way to a more reliable product. So thank you again, everybody. Have a great rest of your day, and we look forward to hearing from you.
Take care.